Okay, welcome you all to this second lecture on our subject, measure and integration. In the previous lecture, we were trying to get an overview of this subject in an intuitive manner. We shall continue with that project. Before getting into formal treatment, let us try to see what is this measure, how measure is connected with integration and so on in an intuitive manner. As I told in the previous lecture, the title itself raises the question, measure and integration raises the question, what is measure and how is it connected with integration and so on. As you can very well anticipate, measure is something to do with measuring, obviously. Why do you want a course for it? What is big deal about measuring? Do you want a rigorous theory for it? That are all the questions that one would like to answer. As I hinted in the previous lecture, some of the earlier measurements are length, area, volume, and so on. If you are in R1 real line, it is natural to attach the concept of length with its subsets. And if you are Cartesian plane, then with objects given in the plane, we associate area and so on. Let us look at R1. In R1, I told you that the most common measure that one would like to deal with is length. But can we talk about length for any subset of R? No. If you have intervals, you can very well talk about length. Okay. So let me consider I to be, capital I, to be the collection of script I. All intervals in R. For instance, given a interval AB, you know its length is B minus A. Therefore, what length does, if you view closely, it associates a non-negative real number with every element in script I. That's what length does if you view it as a function. So you can say L is a function from script I to, let us say, R. I have to slightly polish this. Suppose I allow the intervals to be of unbounded. Say, for instance, I can take entire R to be an interval. In that case, as you know, the length is infinity. So I would like to allow the length to be infinity as well. So I will treat L as a function from I, the collection of all intervals in R, to R star, where R star I mean R union infinity. To be more precise, I don't want R, I want only non-negative reals. But I will adjoin it with infinity so that I can deal also intervals of infinite length or unbounded intervals. And what L does is, for every I in script I, every interval in I, it gives you a non-negative real number, with the understanding that infinity is treated as greater than 0. So this is what length does. But if you observe, the domain is restricted. It is not collection of all subsets of R, but it is collection of all intervals in R. Just to check whether everything goes fine. Can you hear me? And are you with me up to this? So far, so good?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yeah, thank you. So this is what length does. As I told you, if you closely watch, the domain is a restricted domain. I can't talk about length for each and every subset of R. Okay, I have talked L on script I, the collection of all intervals. Okay. Now we want to generalize this concept of length. We wish to generalize the concept of length. Why do you want to generalize? That question, let us postpone and accept that there are some advantages by generalizing the concept of length available in R. Similarly, area available in R2 and so on. So what exactly I am looking for is, instead of a function small l from script I to R star, I am looking for a function, let us say mu, from, to be ambitious, I can start with 2 power R, the power set of R, and I can look for a function mu from 2 power R to R star. Okay. We are looking for, all these things were told previously as well. We are looking for a function mu from 2 power R to R star, or R plus union infinity, where R plus I mean collection of all non-negative real number. Okay. Such that mu of A is greater than or equal to 0 for every A in the power set 2 power R. As I told you in the previous lecture, if you want to just define a function, there is nothing great deal about it. You can always do that. But then I want mu to be a generalization of length. Keeping that in mind, the properties that length satisfy will give me some principles or a guiding principle how I should define my mu. So our experience with length will tell you what are all the properties that we are looking for mu, so that mu can be considered as a generalized version of length. For instance, if I take my A to be interval, mu of A, I want to coincide with L of A. Obvious, then only I can call the new concept as generalization of the length. And of course, it should be defined for sets other than in the script I. Do you follow?
Yes,
This
sir.
Yes, sir.
happened last time also.
Yes, sir.
Yeah. So In short, our own experience of working with the length will guide us what are all the properties that we want to impose on mu. This was hinted in previous lecture. I wanted to talk more about it first. Okay. As I told you, the properties of length and the problem that we are looking at will tell you that mu cannot be defined as you like at any place. There may be some constraints. Mu should be defined like this only on set X. For instance, on interval, it should be defined like length only. Similarly, mu should be defined like this only in a set Y. And those two constraints may automatically tell you that mu should be defined in a particular fashion in some set to set. You don't have freedom. One thing to keep in mind. Another thing is that if mu is to be defined in a particular way on a set X and a particular way on a set Y, consistent with these two, we may not be able to define mu on some other place set. That can also happen. So what I am trying to say is that, therefore, trying to define mu on 2 power r so that mu has properties of length is too ambitious. And therefore, we may not be able to extend it to every subset of R, but a suitable subset of R. Okay. So let me just point out that, however, since experience with length provides some guiding principles to define mu, one may not be able to define mu on 2 power r. Of course, if we can, well and good. But if we cannot, you should look for some suitable collection of subsets. But on a suitable collection of subsets of R, that suitable collection I am calling as B. Say B. So what we are looking for is, thus we need to define a function mu from B to R star, such that mu of A is greater than or equal to 0 for every A in B. To start with, I want mu to be non-negative. Okay. Now there are questions. I told you that our experience with the length, or in general length, area, volume, etc., will provide some hint over what are the conditions that I have to impose on mu. We want to discuss more about what are all the conditions that we will impose on mu. And secondly, I have told a suitable collection of subsets. What is that suitability? Okay. It should be rich enough. For instance, if you want to talk about generalization of length, this B should definitely contain Can you complete my statement?
All intervals.
That is script I. Script I. B should definitely contain I, and B may reach up to 2 power R. We don't know. So it should be rich enough to include script I. Sometime it may not be rich enough to include entire 2 power R. So in between these two, we want to find something. If you are working in R and length, in the other cases, similar things happens. Okay. So this is what the point that we mentioned in the last lecture. Now let us try to abstract it. I told you in the course, first I will deal with Lebesgue measure, and then I will talk about abstract measure and integration. What Lebesgue did was this. The idea is this. He wanted to generalize length. Because of some reason, he wanted to generalize length, and he was looking for a function from B to R star, where B is collection of subsets of R. But then once Lebesgue came with this theory, it was abstracted to cover many other sets. So what I want to say is, why only R or R2 or R3? Let us talk about a general set. More generally, you are given with, suppose omega is a set, not R or R2 or R3, some sets is given, non-empty set. I want a measuring system on omega. By a measuring system or a measure on omega, we mean, can you tell me? Just try to generalize. Instead of R1, we are working with omega. We mean, what you want to do? I want to define a function mu. From where?
Omega to R star.
No, it is not for omega. See here. When you worked with the R, collection of subsets of omega, right? It may be 2 power omega, the power set itself, or it may be some subsets of power set. Okay, so I will write mu from B to R star such that mu of A is greater than or equal to 0 for all A in B, where B is a suitable collection of subsets of omega. Subsets of omega. So this is what in abstract sense measure does. Given a non-empty set, you want to measure all possible subsets of omega. Well and good if you can measure all subsets of omega. Otherwise, some suitable subsets of omega you should be able to measure. Meaning, we should be able to find a function mu from B to R star such that mu of A is greater than or equal to 0 on a suitable collection of subset. Just mu of A greater than or equal to 0 is not enough. Mu should satisfy certain conditions, and that conditions will be governed by our experience with length, area, volume, and so on. Okay. Further, mu satisfies some principle or some rules or axioms or properties, and these properties are governed by or dictated by our experience with standard measure. So we have not done anything new today so far. Instead of working with R, we have slightly generalized into omega. Now, in the rest of this lecture, what I want to concentrate is repeatedly I am telling some suitable collection, and repeatedly I am saying that mu should satisfy certain property. What are the properties that we are looking for in mu, and what are the suitability or richness we want on B? That are the two questions that I would like to answer. Okay. And remember that they go hand in hand. One will give you some condition on the other and so on. We will see. Okay. So I think the questions are clear. Now the questions are, when you say suitable subset, what are all the conditions you need on this B? And what are all the conditions that you are looking for mu, so that it can be called as a reasonably good generalization of the concept of length, area, volume, and so on. Okay. For that, one thing I have hinted in the previous lecture itself. One of the basic principles that we want is sum of individual disjoint parts should be equal to the measure of the whole. Okay. So to put in layman's language, whole is equal to sum of
Its parts.
disjoint parts, finite number of parts. Sum of finite number of
Disjoint parts.
disjoint parts. Okay, good. Finite number of disjoint parts. That means if I can measure E1, E2, E3, and so on, En. Suppose I can measure this. I know length of a small interval. I know length of this much. I know length of this much. I know length of this third part. Then I know what is the length of the whole. Okay. So translating it, if E1, E2, etc., En are disjoint, pairwise disjoint, I mean. Okay. Then what we are looking for is then mu of union Ej, j is equal to 1 to n. I want to be equal to summation of mu of Ej. So this will give one condition that we are looking on mu, so that it can be called as a generalization of standard measures we know. But if you closely watch, this demands something on B, the collection of sets. Suppose I can measure E1, E2, etc., En. That means E1, E2, E3, etc., En are in B, because mu is defined from B to R star. So if E1, E2, E3, etc., En are in B, I want to talk about mu of their union. Therefore, this union should be in
B.
B. So that gives me a condition on B. This automatically tells that B should be rich enough to include union of finite number of elements in B that are disjoint. So just by the underlying principle, whole is equal to sum of finite number of disjoint part, we got some condition that is to be imposed on mu, and that automatically gave what B should satisfy. At least one condition that B should satisfy. Okay. Now, let us again relook the experiences that we have in measuring length, area, volume, etc. And that will give us more and more insight to what are all the properties that I have to impose on mu and what are all the properties that I have to impose on B to define so-called measure. Towards that, now let us move from R1 to R2. And suppose we are interested in finding area. In particular, let us say I want to find area of a circle. I know you all know a formula for that, but I don't want you to tell me that. But tell me what is the underlying principle in finding area of a circle? Or to be precise, area enclosed by a circle. What is the underlying principle? How do you find area of a circle? Don't say pi r square or whatever. Can anybody remind me? The process underlined in finding area enclosed by a circle.
Sum of circumferences.
Okay, so roughly it is right. I think this is what you meant. Okay, so let me proceed. Suppose you are given with a standard square, a square whose length and breadth are of standard length, let us say 1 centimeter. So you are given with this. Now using this, can you measure a rectangle whose length is m centimeter, let us say, and length is m centimeter and breadth is n centimeter? Can you do that?
Yes, sir.
You fill this, right? You fill this square into the rectangle. That's what the idea. And how many squares will be needed? Mn squares will be needed. That is why you are saying the area of this rectangle is Mn square centimeter. That square comes like that. The standard unit of measurement is this in the case of area. Now you try to find the area of the rectangle by filling these squares. So once I have a standard square, I can get area of a rectangle. So I know how to measure rectangle. Area I will call as measure. That is the standard measure in R2. So now I know how to measure rectangle. Once I know how to measure rectangle, I know how to measure right-angled triangle. I am just reminding you the geometry, how it went on. Is it right? Once I know how to measure rectangle, yes, I know how to measure right-angled triangle. Half of it, right?
Yes, sir.
Yes, sir.
Once I know how to measure right-angled triangle, I know how to measure any triangle. Because any triangle you can split into, let us say, 2 right-angled triangle. Yes or no?
Yes, sir. Yes, sir.
So now I have reached up to triangle. Once I know how to measure triangles, how to find the area of the triangle, I know how to measure or how to find area of regular polygons. Polygons you can divide into several triangles. Join to the center. Each vertex you join to the center, for instance. So now I know how to see how it developed from the very elementary standard unit of square. We went up to polygons. And the basic idea to define measure of a polygon is triangulation. You divide into several triangles. Okay. So we went all the way up to polygons. Now, if you remember, to measure the circle, to find the area of the circle, what we do is we inscribe a polygon inside the circle. Yes or no?
Yes, sir. Yes, sir.
And try to make this inscription better and better. Do you get me?
Yes, sir.
Yeah.
Yes, sir.
So what we do is, if you want to measure some object, so the principle is this, the underlying principle in finding the area of the circle goes like this. If you want to measure a unknown object, place a standard object which you know to measure inside that unknown object and try to make that inscription better and better, bigger and bigger. Okay, so you have a circle. I don't know how to find or measure that circle. Inside that circle, you put a polygonal which you can measure and then make this polygonal bigger and bigger. Okay, and this is the so-called method of exhaustion. In geometry, people call it as method of exhaustion. Okay, never bother about the spelling. You can check it. Method of exhaustion. Okay. Yeah. So this gives you, so take this as the second principle. This is one experience that we have from measuring area, volume, etc. So if you have to measure a non-standard object, place a standard object which we can measure inside it and make slightly bigger and bigger so that the object to be measured is got exhausted, and so that you will get the measure of the object to be measured as limit of measure of the standard objects. Does it make sense?
Yes,
Yes, sir.
sure.
Yeah. Now, can you translate this in the language of sets? So what are you having? You have, let us say, E1, E2, E3, E4, etc., which are all measurable. I know all these things can be measured like polygons. And one is contained in the other. They are becoming better and better. E1 is contained in, E2 is contained in, E3 is contained in, etc. Okay. So let me write it like this. Suppose the method of exhaustion gives us this idea. Suppose, or method of exhaustion translates to this language. Suppose E1, E2, E3, etc. are such that E1 contains, E2 contains, so on. They are becoming successively better and better. En contains, En plus 1 contains, etc. Okay. And suppose all these E1, E2 are standard object. I know its measure. That is, I know mu of En. Okay. Now what I am doing is I am approximating a non-standard object, the limit. And can you talk what will be the limit of this set? E1 is contained in, E2 is contained in, etc. Where it will go to finally?
Union of all the sets.
Union of all these sets. Those who are again finding it difficult, try to compare it with the increasing sequence of real numbers. Of course, even E2 are not real number, they are sets. But if you have an increasing sequence of real number, x1 less than or equal to x2 less than or equal to, etc., you know that it will converge if it is bounded above. And where it converges to? It converges to the least upper bound, right?
Sir. Yes, sir.
A monotonic increasing sequence is convergent if it is bounded and it converges to the least upper bound. So the limit is upper bound. Instead of R with less than or equal to, here you are working on a poset, partially ordered set, if you know, with the relation as inclusion. Okay, so you also have a chain. It is like a monotonically increasing. E1 is contained in E2 is contained in etc. So where this will tend to, it will tend to the upper bound, least upper bound. And what is upper bound of all these sets? Union. Union of these sets is the upper bound. And in fact, it will be the lowest upper bound. Okay, so LUB will be union. So what I am saying is, if I can measure E1, E2, E3, etc., En, I wanted to measure the limiting set. That is the set which these things approximates. And the limiting set is here union. So I want to measure union. Union n is equal to 1 to infinity En. Okay, that is mu. And our experience says that mu of union n is equal to 1 to infinity En. Measure of circle should be limit of the measure of the polygons when the polygons become better and better. Are you with me?
Yes.
Yes, sir.
So can you tell me what I want? Mu of union n equal to 120 En. I want to be equal to
Summation of En.
y summation.
Limit of summation of En.
Limit of summation or limit of mu En.
Limit of mu En.
Limit n tending to infinity mu of En. I told it is successively becoming better and better. Therefore, the area of this should be is equal to how this polygonal area behaves. Okay, so mu of union n equal to 1 to infinity En. I want limit n tending to infinity mu of En. So this is one requirement for mu that we obtain from the method of exhaustion. However, this demands something on our B, script B, what it demands. If E1, E2, E3, etc. are in B, if it can be measured, and En is contained in En plus 1, then can you complete my statement? This let me repeat, this automatically gives you a requirement on B, requirement on collection of subset. What is that?
Countable union.
Yeah, see, you are talking about mu of something means that something should be in B because I want mu to be defined from B to R star, right? So if even E2, E3, etc., En are in B, what is the guarantee that union is in B? I don't know. So that I have to guarantee. Okay, not countable union, I can say, because ENs are not arbitrary. En satisfy En contained in En plus 1. So let me write like this. This demands that if E1, E2, E3, etc. are in B such that En is contained in En plus 1 for every n, then union n is equal to 1 to infinity, should be in B. This is why I told the experience with working length, area, etc. will give what condition you have to impose on mu, and that automatically will tell you how much richness you want on B. That they go in hand. Okay. So the principle of method of exhaustion tells us that if at all we are looking for a nice generalization of earlier measurement, I want mu to satisfy mu of union is equal to limit mu of En, not for any En satisfying these conditions. Okay, successively becoming better and better. In that case, that will automatically tell you what is the condition that I am looking on B. Okay, give me 1 minute. I will be back. So far, so good.
Yes, sir.
Yes, sir.
So what we are, so let me tell you, what we are trying to do is, we are trying to get a generalized version of length, area, volume, etc. And put in mathematical language, we are looking for a function mu from a suitable set B to R star, where B is collection of subsets of omega. It can be R, it can be R2, or it can be anything else. Now, the question is, what is the suitability that we are looking for B, and what are the requirements that we want to impose on mu? For that, we are just reviewing our own experience of measuring length, area, and so on. First one was whole is equal to sum of the parts, and second one was method of exhaustion. Okay. Now, before proceeding with what are all the other requirements that we should impose, let me tell you a few things here itself. Let us note the following. So this is one thing that we want on B. So I will put this is B2. The second thing I want on the script B, and this I will call mu2. No, that will be confusing. So this will be 2 and this will be 2 dash. And this will be 1 and this will be 1 dash. So 1 gives you a condition on mu, 2 gives you another condition on mu. Parallelly, 1 dash gives you a condition on B. B should be close to contain unions, disjoint union. And 2 dash gives you condition on B. So 1 and 2 are condition on mu, and 1 dash and 2 dash are condition on B. Okay. So let us note the following before proceeding. Let us note the following. Suppose I have E and F, and suppose that I can measure these two. I can measure these two. Okay. That means E and F are in B, suppose. And suppose E is contained in F. E is contained in F. Again, can you tell me, from your experience of measuring length, volume, area, etc., what is the connection that you want between mu E and mu F? F is larger than E.
Mu E less than equal to mu F.
So yeah, it's a natural demand, right? The measure of smaller subset should be less than or equal to measure of the bigger one. Okay, we need mu of E less than or equal to mu of F. This is from our own experience of measuring length, area, volume, and so on. So this I will call as 3. Okay, let us relook 3. Is it really needed to impose, or it will be automatic? Can I write F as E union F minus E?
Yes, sir.
Yes, sir.
Yes. Now, so this is happening. E, this is E, this is F. So along with E, you adjoin whatever is not available in E. Now, these are disjoint. E and F minus E are disjoint, right?
Yes. Yes, sir.
Yes, sir.
And you already imposed that the disjoint unions measure should be sum of the individual measure. That is the first condition. Sum whole is equal to sum of the parts. So mu of F should be equal to mu of E union F minus E, but that will be equal to mu of E plus mu of F minus E. Are you with me?
Yes, sir.
Now, mu is non-negative. Mu, you want mu of anything to be greater than or equal to 0. So what this tells you? Mu of F is greater than or equal to mu of E, because each quantity is non-negative. So what you are adding with mu E is non-negative. Therefore, mu of F is greater than or equal to mu of E. So if E is contained in F, mu of E is less than or equal to mu of F, you don't have to impose. You will automatically get it. Are you with me?
Yes, sir.
So 3, I am not going to impose. No need to impose. No need to impose 3. 1 will automatically give 3. Impose 3. Okay. But then why did I tell this? But if you see, if you want to do all these things, I can measure E, I can measure F. Then I want to measure F minus E, because I am talking about mu of F minus E, right? And what is F minus E actually? F intersection
F intersection E.
E. Okay, forget about this. No, okay, forget about this. I don't want it to write in terms. I can write it in terms of complement, but right now I don't want it to write it in terms of complement. You can say that if you want to talk about mu of F minus E should be in B. So B should be rich enough to include difference of two sets. Otherwise, I cannot talk about mu of F minus E. I can't do all these things. Okay. So certain thing is assumed here. What is that certain thing? If B includes two sets, I want B to include their difference also. And their difference can be written as, in terms of complement, how do you write? F minus E.
F intersection.
Can you write it in terms of intersection and complements?
F intersection E complement.
F intersection E complement, right? E complement. So, and then you wanted to talk about measure of all these things. Therefore, B should be rich enough to include what?
Complement.
Complements. B should be rich enough to include complements. Okay, keep that in mind, but let me write only this thing. Here, we assume that, so we need no need to impose 3 if we assume the following. It will be automatic. 3 will be automatic if here we assume B is rich enough in the following sense. Since I am talking intuitively, I am making rich enough those type of language. Okay. E comma F in B should imply, forget about whether E is contained in or F is contained in E now. Once E and F are in B, if I can assert that their difference is in B, then I can do all these things. Okay. Now, let me also point out the following. Suppose I have null set. Suppose I have null set. Null set, I can write as null set union null set, and this is disjoint. Okay. So mu of null set will be is equal to mu of null set union null set. If I can measure mu. And this is mu of null set plus mu of null set. So what this tells about mu of null set?
0.
U of set.
0.
Okay. Therefore, mu of null set should be equal to 0. Okay. But if you want to talk about mu of null set should be in
B.
B. Okay. So this demands null set is in B. This I will put as 3 dash, for instance. Not I lost track of number. So this demands 5 is in B. Let us put 3 dash. Okay, we will see. Finally, I will collect all these things. And this I will put as 4. This is whether it is a requirement or a property that will be automatically followed, we will see. But mu enjoys this property. Okay, mu of null set is equal to 0. If you have an empty bottle and you are asking for what is the volume of water in it, volume is 0. So mu of null set is equal to 0. Okay. Now, before proceeding, let us look at method of exhaustion once again. In method of exhaustion, the object that we want to measure, we are trying to approximate by better and better object inside it. Yes or no?
Yes, sir.
Yes.
Why inside? Why always inscribe? You can also circumscribe. That is, the object you can place inside a standard object which you can measure and make that standard object whatever you want to measure, you put inside a bigger one which is easy to measure and make this bigger circumscribed one as smaller and smaller. Are you with me?
Yes, sir.
See, instead of finding area by subscribing with the polygon, inscribing with the polygon, what you can do is put this circle inside a bigger polygon and make those polygons smaller and smaller. It's just the dual. It's just the dual of what you have done. Okay. So let us look at that. Look at dual of method of exhaustion. Method of exhaustion. Okay. So there we were considering E1 contained in E2 contained in etc. Successively better and better in the inscription form. Now we want to make subscription. Okay. So that means we want E1, E2, E3 etc. are such that E1 contains, E2 contains, E3 contains, etc. En contains En plus 1. So this is something like monotonically decreasing. Okay. What will be the limit? Compare it with the real number. Lower bound, right? Lower bound or greatest lower bound to be precise. And lower bound of all these things will be intersection, the set which is there in all these things, that is intersection. So I want mu of intersection n is equal to 1 to infinity to be equal to what?
Limit
Limit n tending to infinity mu en. Okay. So question is, why only always inscribe? Why not subscribe? You can do that and you will get this. But then, okay, before that, this also gives you some demand on B. This demands B is rich enough in the following sense. In the following sense. Can you tell me?
Contains the intersection.
Not for any ENs. If EN satisfy this chain, okay. If ENs are in B, an element of N, En contains En plus 1 for all N, then intersection N is equal to 1 to infinity En, should be in B. So this gives you a demand on B, and this gives you what is the condition that is I should impose on mu. But unfortunately, though this is a dual of method of exhaustion, that is not a nice thing to expect. Okay, that is not a nice thing to expect. Why? Let me give you an example. Suppose I take in R1 length as my measure and consider E1 to be 1 infinity, E2 to be 2 infinity, E3 to be 3 infinity, and so on. Okay, E1 as 1 infinity, E2 as 2 infinity, and so on. Okay, so what is the intersection? If you intersect E1 and E2, 1 to 2 is removed. If you take E1 intersection E2 intersection E3, 1 to 3 is removed, and so on. So what is intersection of ENs?
5.
Null set. Note that intersection of En is equal to null set. N is equal to 1 to infinity. Okay. What is mu of each En? Measure. Here measure is length. Length of each En is
Infinity.
infinity. Okay, and what is measure of the intersection? That is same as measure of
0.
null set, 0. So if you demand this, you will get into trouble. You will get 0 equal to limit of a constant sequence where each one is infinity. Are you with me?
Yes, sir.
Yes, sir. Yes,
So
sir.
what does this example tells you?
So we cannot take this property.
We cannot expect this property. We cannot impose this property, at least when mu of something become infinity. The issue here was mu of E1, E2, everything was infinity. Okay. Of course, if one mu of En is infinity, all other mu of En will be infinity after that because of this chain condition. Okay. So what I'm saying is this. If at all you want to work with the dual of method of exhaustion, you cannot expect it to hold in general, right? But especially when mu of En become infinity for some En, other cases you may be able to expect. In general, you cannot expect. Okay, let me write that. Thus here, mu of intersection En is equal to 0 and limit n tending to infinity mu of En is equal to infinity. Therefore, message is that dual to method of exhaustion. What is the dual to method of exhaustion? Let me name it. That I will name as star. Star cannot be expected in general. Cannot be expected in general. Okay. Especially when measure of En becomes infinity. If it is less than infinity for all n, things may be different. Okay, so let us consolidate our development so far. So we wanted to define a measure which is a generalized version of length, area, volume, etc. So what actually we are looking for is a function mu from collection B to R star, and our experience tells us that the mu should satisfy certain condition. Hand in hand, B should meet certain requirement. So let me write those requirements on B and as well as requirements on mu. Okay. Requirements on mu. Requirements on mu. Let me write one by one. Mu is a function from B to R star. Okay. 1. Mu of null set. What do you want?
0.
0.
0.
2. Obviously, I want measure to be non-negative. Mu of E is greater than or equal to 0 for every E in P. Okay. Third, the underlying principle is the whole is equal to sum of finite number of disjoint parts. Mu of union Ej, J is equal to 1 to N, is equal to summation J is equal to 1 to N mu of Ej, where Ej's are disjoint. Ej's are disjoint. Okay. 4. The method of exhaustion tells us that if you have a non-standard object, it should be measurable by approximating with a standard object increasingly better and better. Okay. So what it translates to, if ENs are such that ENs are in B, that means each one is measurable. It is standard object. And E1 is contained in E2 is contained in etc. Then we expect mu to satisfy this. Mu of union En. This is what ENs can approximate. Is equal to limit the set which En can approximate is union En. Limit n tending to infinity mu of En. This we expect. Okay. And this is sometimes called continuity from below. Okay. Continuity from below. You can approximate the non-standard object by objects lesser than that. You can go on making this approximation better and better. Then the measure of this standard object will tend to measure of the non-standard object which you are trying to measure. Okay. So this is called continuity from below. And you have seen that continuity from above we cannot expect. Are you with me?
Yes, sir.
Yes, sir.
And one more condition that we have on mu is that mu is monotone. If E is contained in F, then mu of E is less than or equal to pure common sense, mu of F, monotone. So these are the requirements that so far we could expect on mu. And this automatically gave some requirement or richness on B. Okay. And requirements on B. Requirements on B. Can you tell one by one? 1. What is B? B is, first let me write, B is a non-empty collection of subsets of omega. Subsets of non-empty collection of subsets of omega, and B should satisfy. Can you tell one by one? If A and B are in B, I want A union B is in B. See, once it is true for 2 sets, it will be automatically true for finite number of sets. So I don't have to say if A1, A2, A3, etc. AN are in B, their union is in B. I don't have to say. This is enough. Once it is true for 2 sets, you can repeat finite number of times. Okay. And second one, what we expected is if ENs are in B for all n in N and En E1 is contained in E2 is contained in etc. Right? So E1 is contained in etc. is contained in En is contained in En plus 1 etc. Then we wanted to measure their limit, namely union n equal to 1 to infinity. That should be in B. Then 3. E is in B, F is in B. Then when you talk about this, the monotonicity, I wanted that difference to be in B. Do you follow me?
Yes, sir.
Yes, sir.
And once you want this to hold, automatically you want in complement. E in B should imply E complement in B. Okay. And you want to measure null set. And you want to say that null set has measured 0. It is a common sense, as I told you. Take an empty bottle and ask volume of water in it. Or yeah, so that should be 0. So if you want to measure and say that null set has measured 0, null set should be included in B, right? So 5 should be in B. So that gives our experience with length area gives you some condition on mu and some requirements or richness on B. Okay. Now let us look the requirements on B. Forget about mu. Let us look the requirement on B. If you see carefully, forget about the how it came and so on. But if you look carefully at B, what B says is that it should be rich enough or self-contained with respect to union. Yes or no? Here it says finite union, and here it says countable union if the collection satisfies this. Forget about collection satisfies this. If your B is rich enough to include or closed under, say, union, intersection, complementation, etc., we are done. Yes or no?
Yes, sir.
So it suggests that we can take B to be rich enough to include or self-contained with respect to standard set operations, union, intersection, complementation, and so on. When I say standard set operation, countable number of times. Okay. Again, I am putting it in a loose manner. Shortly, I will make it precise. If we observe the demands on B or requirements on B, we see that it is enough to ensure B is self-contained with respect to standard set operations. When I say standard set operation, with a countable number of times. If I have countable number of elements in B, their union is in B. If I have an element in B, their complement is in B, and so on. And this is the concept of sigma algebra. Okay. This is what a sigma algebra is. So it naturally pop up. The sigma algebra concept is for defining a measuring system on an arbitrary set to mu. Are you with me? You want to have a B. What is the suitability on B that leads to the concept of sigma algebra? Is it okay?
Yes, sir.
Now I will
Yes.
define what is a sigma algebra definition. So now we got a right candidate to work. If you want to have a measuring system on a set omega, the right candidate to work on, that is right choice of B, is a sigma algebra. What is sigma algebra? It is some collection of subset with all these properties. It should be self-contained. You should be able to talk about countable union. You should be able to talk about complementation. You should be able to talk about intersections and so on. Okay. So let me write the precise definition now. Definition. Let omega be a non-empty set. A sigma algebra. Sigma always in mathematics stands for countable. Okay. Sigma algebra B is in real analysis. Have you heard about F sigma set and G delta sets?
Yes, sir.
Yes, sir.
So sigma always meant for countability. B is a non-empty family of subsets of omega which satisfies the following condition. Which satisfies. So I am defining a sigma algebra in precise term. A sigma algebra B is a family of subsets of omega which satisfies. Can you tell me the requirement? Now you should be able to make the definition. I want to measure null set and tell that measure of a null set is 0. So if I want to measure null set should be in
B.
Sigma
B.
algebra.
So that is first condition that I impose. Null set is in B. Second, if A is in B, that should imply its complement is in B. So that I can talk about the difference. Once I have difference, I can talk about mu of smaller set is less than or equal to mu of larger set and so on. And 3, an belong to B, n element of n. If each an is in B, that should imply union n is equal to 1 to infinity is in B. Once this is there, now I can also talk about the mu of union, etc. If E1 is contained in E2 is contained in, etc. Here we are not imposing that condition. B is rich enough to include union of countable number of elements in this. So these are the requirements you will impose. I don't have to impose intersection. That will automatically follow. Yes or no?
Yes, sir.
Because of De Morgan's law and complementation. I don't have to impose that if A1, A2, A3, etc., AK are disjoint, then their union is disjoint. That will follow from the last one. Once countable union is there, finite union of disjoint sets also will be there. Yes or no?
Yes, sir.
How does it follow? If you want finite union, say A1, A2, A3, etc., AK, take other things as null set. A1, A2, A3, AK, null set, null set, null set, and so on. And take countable union. You will get finite union. Okay. So I have written so many conditions on B initially, but if you select B satisfying this, all those conditions will be automatically satisfied. Okay. So the right candidate to work on to define a measure is a sigma algebra. So far, so good.
Yes, sir.
And in fact, you can see that power set is an example of sigma algebra. Take omega to be any set and B to be 2 power omega. Then it will satisfy all these conditions. But only thing is that it is too rich. to include every set. And sometime measure we may not be able to define on it. So we want a right sigma algebra, not just power set. Okay. Now let us look at the requirements on mu. Requirements on mu. Okay. Look at 3. What it tells? Basically, it tells that the measure of whole is equal to sum of measure of finite number of disjoint parts. Now, what I ask is, can we push it to not finite but countable? Instead of asking mu of union j equal to 1 to n ej equal to sum, can we ask mu of j equal to 1 to infinity is equal to sum for disjoint? Okay, that's the question I wanted to ask. So let me write like this. Look at requirement 3. Look at requirement 3 for mu. Let us try to push it. Mu talks about finite union. Let us try to push it to countable union. And demand the following. Demand the following. The following. So what I am going to demand is this for the time being. Then we will see why this demand and so on. If ENs are measurable, ENs are standard object, n belong to n, and ENs are disjoint, ENs are disjoint, I want to ask whether measure of union n is equal to 1 to infinity is equal to summation n is equal to 1 to infinity measure of en. This is not a method of exhaustion. In method of exhaustion, you had successively better and better approximation. E1 contained, E2 contained, etc. Here we are not imposing that condition. For any arbitrary disjoint sets, whether we can demand this. Is what we are going to do is clear or what?
Yes, sir.
So please show your face sometime, respond to the questions. Otherwise, it is very difficult. Sitting in a room, looking at 4 sides of the wall and go on speaking is very difficult. You should understand this online mode, and you should please switch on your video. At least when asking questions, no, you feel free to answer. It is not to judge your knowledge. It is just to see whether everything goes fine or not. Sometime I may go on speaking without knowing that the internet has some issue. So those things also I should take care, right? So please cooperate. Yeah. So 3 talks only about the finite union. This is 3, I mean. And the underlying basic principle is the measure of the whole is equal to sum of the measure of the disjoint parts, finite number. That I am trying to push to countable number. See what happens. Okay, let us see what happens. So I will call this as Q. This is a question. So Q. Let us examine Q. Still, after telling this much, even one student did not switch on the video. So good. So what you are asking in Q is, you have a disjoint sequence of sets, ENs, okay? We have a disjoint sequence of sets. En. N in N. When I say disjoint sequence, they are pairwise disjoint. Okay. Now let us see what happens. Okay. I have a question Q. Can we, if ENs are disjoint, mu of En, suppose I impose this. So can we have something from that? You take Bn to be equal to union of Ej. J is equal to 1 to N. Does Bn make sense?
Yes, sir.
Because of the demand on B, if EJs are in B, union J equal to 1 to N, EJ will be in B. Okay. By our demand on B, Bn's are in B. Do you see that Bn is contained in Bn plus 1?
Yes, sir.
Yes. So you can use the property 2 or demanded on B. Requirement demanded on 2 demanded on B. Okay. Therefore, by requirement 2 demanded on B, we have mu of union N is equal to 1 to infinity Bn is equal to limit n tending to infinity mu of Bn. This we have because Bn's are chain method of exhaustion. Now, do you see that unions of all Bn will be same as unions of all En?
Yes, sir.
Yeah. So that's quite obvious, right? That implies mu of union En, n is equal to 1 to infinity, is equal to limit n tending to infinity mu of Bn. This much we have. Okay. So with the requirement 2, we have this. But what we asked is, can we have mu of union n is equal to 1 to infinity En is equal to summation n equal to 1 to infinity mu of En. To complete the question, let me add, can we have this? This is the question we asked. Okay. But now we got mu of union En is equal to not limit of mu of En, we got limit of mu of Bn. Okay, so let us look at mu of Bn. Mu of Bn is equal to mu of union J is equal to 1 to N Ej. Yes or no?
Yes, sir.
Yes,
By
sir.
the definition.
Yes, sir.
And can I write this as summation J equal to 1 to N mu of Ej? Ej's are disjoint. And for finite union, we have already demanded it. Where did we demand it? That is actually 3. Demand 3 of on requirement of mu. Okay, demand 3. If I am making some mistake in the, this is not requirement 2, I think. Requirement, yeah. This follows from demand. Can you tell me the number? Mu of union n equal to 1 to infinity Bn. I keep track of the numbers. That's why. How does this follow? How does this follow? How does this follow? Limit mu of union Bn is equal to limit n tending to infinity mu of Bn. How does this follow? This is from which requirement?
4.
Requirement
4. Requirement 4 on mu. Requirement 4 on mu. 4 on mu. Okay. And this is requirement finite unions. disjoint. Whole is equal to sum of finite number of parts. Requirement number, can you tell me? 3, 3, 3 only.
Yes, sir.
Yes, sir.
So using 3 and 4, I got up to this. Now, so mu of Bn is this. So can you tell what will be limit n tending to infinity mu of Bn? Will be equal to limit n tending to infinity summation j is equal to 1 to n mu of Ej. Remember, all these things are real numbers. So now it is something like limit of sequence of partial sums. It is limit of sequence of partial sums. Of which series? This is equal to summation j is equal to 1 to infinity mu of Ej. Yes or no?
Yes, sir.
Yes, sir.
So now combine what we got. Mu of union En we wrote as limit mu of Bn, but limit mu of Bn coincide with the summation. That is we get mu of union En is equal to 1 to infinity is equal to summation n is equal to 1 to infinity mu of En. And this is what we were asking in Q. Can we emboss? That's what we were asking. So can you conclude? What did we do so far in this? If I use requirement 4 and requirement 3, that will automatically give me requirement 3 and requirement 4 will automatically give me
Question requirement. Q.
that I have defined as Q. Are you with me? So let me just write like this. 3 plus 4, 3 plus 4 in requirement of mu implies Q, requirement in Q. It is straightforward. Now I am giving you an exercise. What is interesting is that the converse is also true. If you require Q, if you put the condition in Q, that will imply 3 and 4. Interestingly, please try to prove it. Okay. Interestingly, requirement in Q. What is the requirement in Q? Union of disjoint, countable union of disjoint. Measure of that is equal to sum of the measure. That will automatically imply 3 and 4. Now, can somebody, at least for my can you tell me what from all these things, what you can deduce? Q, one single condition I wrote on Q is equivalent to what? Equivalent to 3 and 4. So why to list 3 and 4? Though in motivation, actually 3 and 4 is more important. Yeah, here 3 and 4. This 3 and 4 is more important. I can cancel this 3 and 4 and I can replace it with a single condition. Okay. But if I have told single condition in the beginning, that does not motivate how things happened. 3 happened because of the underlying principle sum is equal to finite number of disjoint part, and 4 happened because of principle of exhaustion. Okay, give me 5 minutes, I am concluding. So 4 happens because of principle of exhaustion. But we observe that 3 and 4 can be combined to a single condition mu. Okay, and therefore 3 and 4 can be replaced with a single condition in Q. Okay, so let me tell you what are all the requirements on mu. Thus, requirements on mu are on mu are 1. Mu of E greater than or equal to 0. 2. Mu of null set is equal to 0. And 3. Two condition I will combine. Mu of union En is equal to summation mu of En. N is equal to 1 to infinity. For not all En, disjoint Ens. For a countable collection of disjoint sets. Element sets in B. Ens are in B. So from length, area, and so on, we listed so many conditions on mu, but ultimately those conditions on mu coincides with or boils down to these three conditions. Are you with me?
Yes, sir.
Yes.
Yeah.
Yes,
And
sir.
the last condition is actually combination of two principles. One is the whole is equal to sum of parts, and second one is method of exhaustion. You can measure a non-standard object by measuring standard object inside it successively, better and better. Okay. And if mu satisfies these conditions, mu is called a measure. I have defined now what is a measure. Okay. Definition. So that's the last point I want to make for today's class. Definition. Let omega be a set and B be a sigma algebra of subsets of omega. Then B will satisfy certain condition I have already told. A function mu from B to R star is called a measure. Is called a measure if mu satisfies the following conditions. Mu satisfy the following condition. 1. Mu of null set is equal to 0. 2. Mu of E is greater than or equal to 0 for every E in B. And 3. Mu of union En, n is equal to 1 to infinity, is equal to summation n is equal to 1 to infinity mu of En for a countable collection En in B that are disjoint. When I say disjoint, Ej intersection Ek is null set for every J and K. So what are the two definitions we made today?
Sigma algebra and measure.
Sigma algebra and measure. Everything is motivated from our experience of measuring length, area, and volume. Sigma algebra is the right candidate to work with, how much rich enough I need for the subset, and measure is the right candidate for abstracting or generalizing length, area, volume, and so on. Is that clear?
Yes, sir.
How is this third demand? Let me just cross check. How is this third demand be motivated? Why we impose mu of union En is equal to summation mu of En? The underlying principle is two. One is that whole you can divide into several parts and you can add finite number of time. And secondly, if you have a non-standard object like circle, and if you want to find its area, you inscribe it circle with the polygons and make these polygons finer and finer. Okay, so combining these two, we got third one. Does it make sense?
Yes, sir.
Yes, sir.
This is the most abstracted thing which we will discuss at the end of the course. Now what we will do is the Lebesgue approach. We will not work with arbitrary omega, we will work with only R. And Lebesgue constructed in a very special manner. A particular mu he constructed, and that is called a Lebesgue measure. We will not talk about arbitrary sigma algebra, arbitrary measure, and so on. That we will postpone at the end of the course. Next time onwards, we will be talking about a particular measure called Lebesgue measure. Okay. One question remains unanswered. Can you tell me what is the question? Still, I did not say. Okay, you want to generalize length. You want to generalize area. You want to generalize volume. One question remains is, why do you want to
Generalize.
generalize? Why you are not satisfied with the length? Why do you want something other than length? Okay. As I told you, there comes the idea of integration. So in the next class, and there comes Lebesgue. So next class, I will tell you why one should go from length, area, volume, etc. to
Listen.
measure. How to go today I have already told with the help of sigma algebra and things like that. Why to go will be answered in the next class, and after that formal treatment of the subject will start. Okay, these are all intuitive understanding. With that, let me stop the recording and leave the meeting. Thank you.